Welcome to today's webinar, SIPI Model Extraction, Everything You Wanted to Know but Were Afraid to Ask. My name is Brianna Curl, and I will be your moderator for today. Before we get started, I'd like to address a few logistics and details on the GoToWebinar platform. If you are unable to hear the presenter or see the presentation at any time throughout the webinar, please let us know in the chat and we will do our best to resolve any issues. This webinar will be recorded. The recorded presentation slides will be posted on the EMA resource page. And once they are posted, we will send everyone who has registered for today's webinar an email with a link to the recording and slides in the next couple of days. With that being said, I want to thank you all for joining us for today's webinar and introduce you to our presenters, Matthew Harms and Roger Chin. Matthew is an application engineer and has been with EMA since 2003. He specializes in design side issues pertaining to part management, circuit simulation, signal integrity, and power integrity. Roger is a field application engineer and has been with EMA since 2013. He focuses on component library management, design data management, SPICE simulation for circuits, and power integrity. Matthew will start off the webinar with a presentation followed by the demonstration given by Roger. Assuming we will have time at the end, we will follow some questions in a formal Q&A. Thank you for your attention, and now over to you, Matthew.
So we're going to talk first about what is extraction and different methods that you can use to do extraction. So this is our overall agenda. We're going to start with what is extraction. So that's the first section that we're about. And what extraction is it's turning of a board. In our case, it could be a package, it could be a chip, but turning something physical that you have design files for into something that you can simulate. So that's overall what you're trying to do with extraction. You're trying to take some CAD file that you have. Normally I'm going to be talking about boards today, but you're going to be taking some file and you're going to be turning it into some sort of model. Normally the models you're going to see, it's not exclusively, but often the models are going to be S-parameter models. So you're going to generate S-parameter models for the devices that you're taking a look at. We'll talk a little bit about what S-parameters are, how they work, and what's inside of them and what they represent. But that's generally what you're trying to do. You're taking your board or your ECAD file, turning it into something that you can model. How is it different from simulation? Oftentimes this is what is wondered. So people wonder what's the difference between model extraction and simulation. Model extraction, you're generating a model that represents what's happening in your board, as I said. Typically they're frequency domain. The results can be the models themselves. So sometimes people just want to take a look at those S parameters and that's enough for them. Or sometimes they want to translate that into a different type of matrix, like a Z or a Y matrix, and you can take a look at that. But you can simulate these also afterwards as well. So if you want to, you can take these models that you've generated and throw them then into a simulator in the next step. When you put them into a simulator, you're going to be stimulating them with models. So you're going to have typically some IBIS models on the receiving side that are putting some signals into your S parameters, and then you're going to be seeing some resulting waveforms that you will determine the quality of your base simulation. If you're doing radiated emissions testing required, if you're doing RF application stuff, that typically towards the end, which is simulation. A little bit about S parameters and what S parameters are. So what is this file format that it's a path generated from extraction? So we'll just take a few moments to talk about what S parameters are. What they are is they're a mathematical model, and you can think of them like a black box that contains a model representing what your channel is going to do if you apply signals to it and take a look at what's coming out of it. And it's similar to something in optics. I have a picture here of optics, and it's just how energy transfers through, what gets reflected back, what gets pushed through, and if there's phase changes associated with that as well. So that's what an S-parameter model tries to tell you. It tries to tell you what's getting reflected back and what's getting passed through and what changes about the signal that gets reflected and the signal that gets passed through. That's what we're trying to find out, and qualify with our S parameter model. And it's then composed of real and imaginary numbers so that it can contain any number of ports. So you can have many signals that are traveling through this. It's very common to have 2 or 4, but you can have hundreds of signals in an S parameter model if you would like to. They are frequency domain based, and they're ASCII readable and not owned by any company. So there's no company that owns the S parameter format. It's a neutral format, mathematical format, and the industry has adopted it, and we use it prolifically. They do also need to define the reference impedance that they're measured in as well, and that's part of your S parameter file. If you want to conceptually try and understand what an S parameter file is, what I have here is I have an example of something like a 10-port S parameter file. So if you had a 10-port S parameter file in that you have 10 signals that you want to create a model for and make a S parameter file to represent it, it's going to look something like this conceptually. So you're going to have those 10 signals, and you can think of them as your inputs and your outputs. So if you send a signal into port 1 or signal 1, how much gets reflected back? That's managed by this S11 in the matrix. So in your S parameter matrix, S11 tells you how much signal is going to be reflected back when you send something into port 1. And you can see these yellow ones down the middle. These are all your reflection coefficients. So these are all the signals that get reflected back when you put something into it. So the orangish ones are the red ones here. This could be any number. It could be any other port that it goes through to. In my case, I picked the 5 later. So S11, and then you have S16, 22, 27, etc. So five ports later. So when you put something in port 1, it comes out port 6. And that would be your insertion loss. So what it's telling you in this case is how much gets lost on that signal just traveling through that channel. So as you put some signal in, some gets reflected, some gets passed through. This is how much gets 1/6 in our case is representing that. And all these other numbers, 1, 2, 1, 3, 1, 4, etc., all those other ones that are white, those ones represent crosstalk. So those are how much signal is going to get put onto a different net. So meaning that if you send some signal into port 1, how much gets transferred onto port 2 and is noise then at the input on port 2 or port 3, port 4, port 5, etc. So how much crosstalk is then put onto those nets. So you can see if you have a large S parameter file, your matrix here is going to get pretty big, and each one of these points, in my case I have 100 of them, each one of those points is represented by a large range of frequency points then as well. So you have your S parameter, and then you have frequency points. So these files can grow quite large, especially if you have really big S parameter files. So you have frequency points for every single one of these S parameter matrices. If you were to take a look at the ASCII file itself, I said it was ASCII readable, and it is. So if you open it up, it's going to look something like this right here. It's going to tell you the frequency point that it's at, measured in hertz. And it's an S parameter RI right here in the header working. It means that the numbers are being expressed in real and imaginary. They could be expressed in magnitude phase or dB phase, either of those 3. In my case, in this screenshot here, it's represented in real and imaginary. So you have 0.03 in real and 0.005 in imaginary. And that's going to be your S11. So that's your first one in your matrix. The next one here is going to be S12, then you have S13, S14, and then S21 because this is a 4-port, and then 22, 23, 24, etc. down the line. And I'm highlighting a couple points for you here that tell you a little bit about what this signal is doing. S12 and S21, these are our insertion loss. So this is the amount of signal that's going through. You can see this number is quite a bit bigger. A lot of our signal is getting through. That's usually as intended. You want a lot of your signal to get through. So it's pretty close to 1, pretty close to everything is getting through on those ports. S143, those are our other ports that are getting through. You can think of it in this diagram as A1 going to B2 and B1 going to A2 or something like that. That's your throughput, how much is getting through. We would have reflection loss would be the top one here, and then it would be the second one right here, and then this one right here. So it'd be the S11, the S22, the S33, the S44. people are going to be most familiar with it looking at a graphic like this one that represents what their S parameter is doing. And what we're taking a look at in this S parameter, just to give you kind of a sense of what they're going to look like. First, we're probably not taking a look at the whole S parameter. It's not that common to take a look at the entire S parameter. Usually you're going to take a look at the transmission, which is also known as the insertion loss, and you're going to take a look at the reflection. And those are the losses that just get reflected back. So those would be the most common ones you would take a look at. You can take a look at the rest of the matrix, but it presents really a lot of crosstalk. And it's very useful for simulation, just a little bit more challenging to gather good information from it when you're just looking at the native S parameter file. What we're taking a look at here, in this case for transmission, the red and the blue are transmissions that we're getting for this S parameter. And you can see that the signal quality degrades as a function of frequency. So as it gets higher in frequency, less of our signal is able to make it through. And you can see a solid color and a dotted. And those represent, and we're going to talk a little bit more about this in a bit, but those represent different ways of extracting the model. So depending on how the model gets extracted, so how this S parameter file gets generated from our model, from our original board file, how that gets generated can have an effect on what type of results we're going to get, the accuracy of those results. You certainly want the most accurate solution at all times, but that's going to come at a trade-off, and we're going to see what that is in a little bit. So the dotted lines are full package analysis, and it has a little bit more information included, a little bit greater accuracy, and the solid lines are a little bit less accurate and more likely faster to get to. So that's a graphical representation of S parameters. What we're going to do next is let's take a look at some of the challenges that are associated with extracting models. So far we saw what extraction is, what S parameters are. Let's talk about some challenges that you might run into when extracting models from your board. The three main items that you're trying to balance when you're doing extraction, you can see on the right there, are time, and that's the amount of time it's going to take your computer to run the simulation. It's going to be accuracy, and that's how accurate your solution is going to be overall. And we saw that on the previous slide. You can have different answers depending on what type of solver you're going to go with, and the size of the shapes to extract. So how large is your board? How much tail is in there? What needs to be extracted from there? And what we're trying to picture here is you can't really have everything. So it's kind of like the pick two scenario where you get to pick, you can have fast simulation and very good accuracy, but hopefully your design size is very small. Then that will work. Or you can have a large design and it can go very fast, but your accuracy is going to be less. Or you can have a large design and get really great accuracy, but it's going to take you a long time to get. So it's kind of that trade-off between those three items that's always in tension with the different techniques that we're trying to use to solve our model. So time to simulate, that's always a hard one. If you're looking at a large collection of nets or a big design scope, it's going to take a longer amount of time. And you'd be interaction between the nets, so you want to see that crosstalk information, so there's a lot of data there. Accuracy of the solution is something that is often very critical for people. They want a solution that's accurate because it doesn't make a lot of sense to run a simulation if it's not going to provide accurate results. So you do need some amount of accuracy, and it gets especially challenging when you get into higher frequencies. To maintain that accuracy as you get into higher frequency simulations, it gets more and more challenging because you have to model more and more things that do become problematic. And the size of the shapes to extract, so the size of your board, if you have a really big design and you want to do everything on that design, doing it fast or accurately are going to become a problem. So you don't get to pick all of those. If you have something very small, no problem. You can do it very fast and you can do it very accurately. But as things scale up, as things get bigger, it gets more and more challenging to simulate that. All right, so what are the effect of having problems when you're doing extraction? There's a number of things that could be problematic. So you could have reduced yields, costly respins, etc. You see these items here. The one I want to focus on is reliability issues. I believe that's the primary reason people are doing extraction, is to reduce field failures and to increase reliability. They want to make sure that the channels they're looking at, the power planes they're looking at don't fail, and especially that they don't fail as a function of time. So as things go longer, you want to make sure that they're not going to fail in the field or once they get out of your control. All right, next up in the agenda. So we saw some challenges. Let's talk about the different types of extraction and when we want to use these different types of extraction. So we're going to speak kind of generally here about the different types of extractions that are available, and we'll see what we can learn about the different techniques and their strengths and weaknesses a little bit. So first is finite difference time. This is a technique that's used to solve problems, and it's important to FDTD as well. The strengths of this one, if you do have a large design, you want to take a look at lots of things on a large design, you want that fast, this type of solver is going to be ideal for you. Its challenges are going to be accuracy at some points, especially some of those high frequency points. It's going to have trouble up there, and it's tough to parallelize the CPU resources. So that becomes something that when you do have bigger problems, you do want to share the load of solving that problem with a number of machines. This solution doesn't lend itself extremely well to parallelization, so it is a bit challenging. The results of this type of extraction are going to be a time domain model, and that is good for some people. So if you're going right off to simulation in a time domain tool, that's not a bad model to get. Oftentimes people want to take a look though at a frequency model for the type of results that it gives you, and the general accuracy you're going to get from a frequency domain model. So this one does not yield that type of model. So when do you use the FDTD? You use it when you have a large design problem. So you have a whole board, you want to do analysis on a whole board and take a look at all your nets on your board. That's when you're going to use a solver like this one. When accuracy is not the major concern, you're not quite worried about drilling into incredible detail yet on specific areas, you just want a general idea of what's going on in your board. Simulation speed is important, so you do want it to go fast, and that's the strength of this type of solver. And you don't necessarily require a frequency domain model, although you can always turn your time domain model into a frequency domain model. Usually if you want a frequency domain model, you'd probably solve in a method that would yield that type of model in the first place. So this is one solver, FDTD. Let's talk about the other end of the spectrum. The other end of the spectrum would be the 3D FEM solving technique. And this is opposite in every way. So this is extremely thorough and accurate. This is using Maxwell's equation, and it can manage any type of design file you have. So it can manage any return path. Return paths can be complex in terms of solving when you don't have solid layers above and below. So if you don't have solid plane layers, that would be, in a solver's mind, that would be a challenging return path. The 3D tool, there is no such problems with that. Vias are also not a problem. Those can be challenging. We'll learn about as well. And it does require just minimal setup. So that would be another strength of this technique. So the shapes that are used to mesh have a tendency to converge well. They're able to map themselves onto the available shapes and converge as well. Pretty nicely at a solution. So the challenges for 3D FEM, with all the strengths it has, and they are substantial, what are the challenges? The challenges, the biggest one is that they're very, very time consuming. Very time consuming to run this type of simulation. So it's very accurate, but it does take a long time to run this type of simulation. So it's not good for very large structures. The larger the structure you have, you remember, the longer the time it's going to take. So time being a challenge, and it is time consuming if you have cross-hatched ground, for example. That's going to be time consuming because this type, it has to mesh all that. A little bit challenging to mesh. It's not going to have problems with it, it just takes time. And it is an intense CPU resource hog. So it is going to need a lot of resources. You're likely going to have to get a special machine to run this type of simulation. It does in modern domain as well, which is generally the type result people want. They often want a frequency domain model because it can be simulated nicely in the time domain, and it can be analyzed in its native format and yield interesting results as well. Okay, so when do you use the 3D FEM tool? When accuracy is of critical importance. So when you're at the sign-off stage, this is the field solver that you're going to want to use. Accuracy is the best. When you have complex paths, so I was mentioning before, if you don't have the plane above, plane below, then it's going to be good for turn for that. It's good for smaller problems. So if you have a fan out that you want to take a look at, it's good for something like that. If you want a frequency domain model, so if you want that S parameter type model, this is going to be a good solver. And if you do have a capable CPU, so you will want something pretty decent to take a look at any reasonably large problem. So recommended specs are a lot of RAM. You can see it is RAM intensive and lots of free space on your hard drive, preferably an SSD, and a decent processor as well. So you can always go more than this. This is what we'd recommend if you want to do any type of substantial simulation on 3D FEM. Another solver that's used is method of moments. So this one is efficient simulations. It's quite efficient and it runs generally pretty well. Challenges are that it's relatively complex to set up. There's lots of complicated equations you need to set to get it going, and it's not quite beginner friendly. It also doesn't happen to be a big player in the PCB or package extraction space. So it's not something that a lot of PCB or package people use, a tool that uses this technology. It is only more dominant though in the IC extraction space. So it's much more strongly used over in that space. So I'm not going to talk about that one too much more. After this, there's hybrids. So hybrid solvers is another technology. So what you're doing with the hybrid is you're using different solvers for different parts of your design. And you're going to solve some things with an FEM type solver. You're going to solve things with the BEM type solver, which we didn't necessarily talk about. That's the boundary element method. You're going to use some for finite difference method, some parts with that. Some you're going to use transmission line solvers. So a variety of different solvers you're going to use, and you're going to couple that energy together with this hybrid solver. So the strengths of a hybrid solver, using different solvers in different portions of your overall design. The strengths over 3D FEM is that it's faster. So you're decreasing the amount of simulation time needed to run this. So it's going to be able to give you results that are acceptable and allow you to move forward. They might not be sign-off level quality, but they'll probably be acceptable. It can handle things like rigid flex boards. So if you have boards that have rigid portions and flex portions, it can handle analysis on that, as well as crosshatch ground. So that can be challenging for hybrids, but they can do those types of analyses. It's ideal for power plane simulations. So this is what it's especially good at. It's really fast for running those type of simulations and generally quite accurate for those type of simulations as well. The assumptions. So it's going to make a few assumptions that are hopefully true. And if they're true, your results are likely going to be accurate enough. If they're not true, then the accuracy of your solution is going to be compromised. So the assumptions that this is making is that it needs a consistent vertically overlapping metal planes on surrounding layers from your traces. So if you're taking a look at traces, they need to have vertically overlapping metals around that trace to make sure that it has return path for it. If it doesn't, some of the assumptions about the strip lines that it's calculating are not going to be true. So you do want to make sure you have lots of metal planes around. Vias should not be longer than a quarter wavelength. So if the vias are long, meaning your board is really, or your frequency is very high, then your vias are going to be electrically long, and that's going to be a problem. If your vias are 1/10 of a wavelength or longer, that's the point when you should start considering using a 3D FEM solver. But if they're over a quarter of a wavelength long, at that point you should definitely be into a 3D field solver. It's also going to assume that you have infinite power and ground planes so that they extend on to infinity, which may or may not be true if you're near the edge of your board and you're going to see some fringing. All right, so when do you use the hybrid solver? when you're doing power plane simulations, that's going to be a good time. When your transmission lines do have that consistent vertically overlapping metal, and crosshatch ground is fine, so that's no problem. And when your vias are electrically small, 1/10 of a wavelength or less, if you have a very thick board or you run at very high frequencies, then that is going to stop being true, and you're going to want to consider using a different type of solver. And when you have minimal via-to-via coupling, via-to-via coupling is something that's challenging to do with a hybrid solver as well. Okay, so those are the different types of extractions. Let's talk about typical methods used to manage extraction of complex structures. So when you have complex structures, how do you manage the extraction of that? And we had talked a little bit about what some of these complex structures are. Complex structures in terms of extraction would be things that maybe don't have those ground planes, maybe have long vias. So 2.5D, or the hybrid solver, is a virtual VNA, vector network, the analyzer for signal integrity and power integrity. It supports the S-parameter extraction, so the frequency domain model, and it can handle more than 500 channels at once, up to 20 gigs. So it can handle quite a lot, this hybrid solver that we have. It can do resonance analysis. That's what you're seeing in that bumpy waveform in the upper right there. And you can have full consideration of power delivery effects. So it's going to be great for that. It can also work on the rigid flex or multi-fabric designs, and that's no problem. The typical question I get asked is, what frequency does the 2.5D or the hybrid solver support? Does it support at which time you should transition to what 3D model? And it's a complicated answer. Let me go over some examples of why it's a complex answer. It's a little complicated because here's an example where we have an RDL, so a redistribution layer, and we have a little package here that we're doing some analysis on. And what we've done is we've done analysis on this using our hybrid solver, and then we did it again with the 3D solver. The 3D solver being what we assume to be the correct answer, and the hybrid solver being verified against that. So the hybrid solver in our case here is the blue trace, and 3D true answer is going to be in red. And you can see that they match each other really quite well up to about 10 gigahertz. So they're doing a pretty good job matching each other till that point. And then after that, it seems that they diverge a little bit and they're not quite following the same path, at which point we would say, if you're over 10 gigahertz, you should probably use the 3D solver. But is this always the case? Can you blanket say, if you're over 10 gigahertz, that's now when you need the 3D? See what happens when we increase the thickness of this. So we're going to double the thickness as well as the previous case, while everything else is the same, and the structure is identical, just increasing the thickness. And you can see now that the answers vary quite a bit. So the red again is our assumed correct answer from the 3D solver, and the blue is what we're seeing now. And here you can see the blue and the red are quite a bit different on both, and they really only match for a very short time. And it might be accurate only to a gigahertz, maybe even less, depending on what you need. So in this case, it's not accurate for very long, just because the vias are getting electrically longer and having the assumptions that the hybrid tool is making is causing problems in accuracy at even lower frequencies than we may have expected. Let's take a look at one more example where we get to see the correlation between the two. So here's a memory bus. We're taking a look at a portion of nets, and we want to analyze them both in our hybrid solver again. So the hybrid solver is blue and red is our 3D, and 3D again is assumed to be the correct answer. You can see that these ones are quite close. These ones are tracking with each other pretty well. The X limit of this waveform is 15 gigahertz, and you might even say they match the whole way. So they're not dead right on top of each other, but they're close enough that you might consider this a match the whole way. So with this, it appears to be maybe working all the way till 15 gigahertz. For that reason, it's tough to give a rule of thumb to say when you should use the hybrid and when you need to stop using the hybrid and go to the full 3D solver. It really does depend on what you're trying to analyze and how that's all set up. So the 3D FEM solver when you're managing a complex problem, the 3D FEM solver is really the gold standard when it comes to accuracy. It's going to subdivide the entire volume into many small tetrahedral elements and then gives them electrical fields and calculates those fields at every point. So it uses the Maxwell's equations to start determining how this is all going to act, and it correlates very, very well against bench verified data and the real world. So it's really the gold standard, this type of solving methodology if accuracy is your goal. It is valid for the whole frequency range. So there's really not a lot of shortcomings to this field solver. It really does everything quite well. Aside from the simulation being slow, it's really very good, accurate almost everywhere. And it's very useful when accuracy is needed to the high frequencies especially. So when you are going to high frequency simulations, that's when other field solvers will often start breaking down. This one will not. So if you're doing serial links over gigahertz, it would bear consideration to start taking a look at a full 3D solver. So how do we start managing some of the simulation being so slow? There's a variety of techniques that we're going to use in our 3D tool to increase the speed. One of them is cut and stitch. And Roger's going to talk to you about a few minutes. He'll show you an example of how that's going to work in the tool. But what it allows you to do with that and just do is break your design into a smaller bit and then even say where you want to use one solver and where you want to use a different solver. So it allows you to use the solvers in their areas of strength and reduce your simulation time that way. So the strengths of the 3D solver is certainly accuracy, and it should be used for sign-off verification. You can use it in that area. It's going to do great there. But accuracy is the #1 thing it's good at. Why don't people use it all the time? Because you can't have accuracy, simulation speed, and a small design size. You can't get all 3 of those. You usually get 2 of those, and the other one is going to be a problem. So if you want your high accuracy, your simulation speed is either going to be slow or the amount of design you're able to simulate is going to be small. So if you do want a large design, you want it to go fast, that is going to be a challenge. What do we do to solve this? I mentioned that we can introduce this cut and stitch method. So we see a picture of it here on the side. And what that allows you to do is cut your area of interest down to a smaller portion. So this is decreasing the size of your problem that you want to solve. We're going to decrease its size by cutting out everything outside of it, just focus our attention on a smaller portion. And then you can even go further and say, well, there's portions that would be fine with the solver. So let's say we want to solve this middle portion here with the hybrid solver, that's going to be fine with the hybrid. But these vias here, we want to use the full 3D solver for that, the breakouts here that we're seeing. So let's see that with the full 3D. And let's do the middle portion here with the hybrid. That's certainly going to increase the speed at which our simulation is run. It's going to run a little bit faster. We also do support multi-threading and distribution. So this can be a solution as well. If you just have a big problem that just needs to be solved, you can send it out to multiple machines or multiple cores on a single machine and just share the load between that. So good extraction, what is good extraction going to give you? It's going to help you to see violations, to streamline, to eliminate valid iterations, and improve time to market. The one I want to focus on here is eliminate multiple validation iterations. Really what you want to do is you want to design it once, get it right, send it all the way through, validate that, and make sure that at the end it's going to be correct. You don't have to loop back and fix any problems because you've simulated and you've verified that it's going to work. So what else can you do with your models that you're extracting? The other things that you can do with your extracted models is you can connect them into time domain simulation as well. So the extraction we talked about can be the end, this is the S parameter or the results of an extraction simulation that we're doing, goal, and some could be the end result. But in other cases, you might want to tie it up to some other models, some IBIS models, and generate some simulation and see some waveforms out of that. So that is something that we can do as well too. To give you a closer look at some of this, we're going to move into a demonstration here.
All righty. Thank you, everybody. So we're going to step inside our cadence integrity tools here to take a look at some of the extraction techniques that Matthew has covered. We're inside of our Power SI tool here, which is our hybrid solver extraction tool. With the cadence integrity tools, you can bring in layout files from all sorts of different CAD tools, and I've already done that here for this board. So when you bring your board in, you'll probably want to verify your stack of information, make sure you have the right dielectric set, the right information pulled in from your board. And then we're going to go into our net manager over here on the right to pick out the nets we want for extraction. So we're going to do 4 bus lanes that are 8 bits each for this demonstration, which is why we're using a hybrid solver. When we step into our 3D solver tool, we're going to probably want to do smaller nets. So to start, I'll pick my ground net, and down smaller number here, I'll have my bit lanes. So 0 to 7 is my first bus lane. I can enable that. And I'll continue 8 through 15, 16 through 23, and then up to 31. So that's 0 to 32. That's our 4 8-bit DDR bus lanes. And we have enabled those nets here. And I'll actually also include a power net, because the Power SI tool can create one model that includes both the DDR, the power nets, so the strobe nets down here. So we have 4 bus lanes, and also we'll have here the strobe timing lanes, and 0 through 3, I'll enable those. And then the positive side, 0 through 3 as well, and enable those. So now we have our nets all enabled, and we're going to want to generate ports. So those ports are our connection points over here that we want to generate for our components. So we have our U1 controller and our J1 and J2 connectors that our DDR buses are running between. So first I'll generate for U1, and I'll see that I have 41 ports generated. So again, we had those 32 DDR buses. We have our power, so that's 33, and then we have the 8 from the strobe nets as well. So you can see here it describes to you each of the connection points on that component U1. And these will be the ports that are used in the S parameter. So we'll do that for U1, and then we'll generate it for J1 on the other end as well. So now 41 plus 41, we have 82 ports there. And then finally for J2, so a total of 123 ports generated from our nets that we have enabled. Once we have these ports generated, we're actually ready for simulation. And for the sake of the demo, I've already done the simulation. I have a fairly average laptop, and it took me about 15 minutes to generate the S parameter file. So let's take a look at that file. So I've already loaded it into our Power SI tool for you. It is in a BNP format, but you can also export and save the S parameter file into your S parameter format. So here we see our return losses, our extraction model. I'm going to start by using the channel filter to remove the power net. Or sorry, for port 2, when we send a signal 2, we want to see our throughput. We can go to the channel filter again, and now change it from return. And we can see here now the majority of our signal is able to go through from each of the ports to their desired port on the other side. And when you hover over these ports, you can see the exact nets and the exact connection points where those nets are traveling. The rest of that file, again, it's the crosstalk data, which is the majority of that file. And it's a very large amount of that data file, so I'm not going to show it here. But I do want to show us let me hide all the curves. I do want to show us the power plane impedance that we were able to extract inside this same model. So I'll turn off all the channels and just show the return loss for the power net. And we can step from the S domain into our Z domain to see the impedance response. And I need to change the scale of our power plane. So this is a bare board. We don't have a VRM model, as you can see from our lower frequency behavior. And we do not have decoupling capacitors on this board yet either to smooth out our higher frequency behavior. But the key is that we're able to generate one S parameter file from our board that includes both our power net and all of our extracted DDR nets as well. So that was our Power SI extraction tool using a hybrid solver. Now let's step into the 3D tool, the 3D solver tool. So here I've designated a smaller area of nets that I've already picked out and generated ports for. And I've marked this area to use for our 3D solver. So we're going to extract this into S parameter model, and we're going to show you how you can save a little time by using our cut and stitch method that Matthew covered. Longer high-speed channel here, and I've already created this cutting zone boundary to designate this area, the cutting boundary add, to draw these points to draw my cutting zone. Now, so here with our vias and our more complex, we're going to use our 3D solvers. Here, where it's fairly straightforward, we can use our high geometries for solver. So let's turn on our cutting zones. So we have the zone, cutting zone 2 here, and we're going to create more zones by splitting them with lines. So I can now go onto my design here, and I can draw split zone. We can draw a line, and now we can see it's automatically created this cutting zone 3 where we're using a different solver. And notice you do want to keep your zones perpendicular to your nets, and notice they do create automatically these internal ports that will connect the different zones together when we create one extracted model. So for this side, over here, we'll create another cutting zone. And in order to create a zone that is, we're going to perpendicular to both traces, we're going to use multiple lines to cut. So I'll go down this way to be perpendicular to that line. And then I'll create a perpendicular zone here. So now we have cutting zone 4 created. We have our cutting zone 2 here. And we can assign the cutting zone 2 to be a hybrid solver because we don't have as complex of geometries and we don't want to dedicate as much calculation time to these power planes. So we want more complex geometries, use a 3D solver and create a zone for it for that side and this side over here. And for the sake of this demonstration, I've again done the simulation beforehand, and even using the cut and stitch method here, it took 45 minutes on my laptop to generate one extracted model for this tool. So let's take a look at our results. There's one file. So again, one file for the 3 zones all concatenated together. Load in this, and we can see our S parameter behavior for this. So if I want to see a Smith chart, I can go to my channel filter and add my insertion loss part, and I'm going to disable all my nets just to show the one I want. So for port 3, that's a return loss back to 3, and then port 3, the throughput to port 7. I'm going to change this from an amplitude plot into a Smith chart, and I can see here our results. We can see this is our insertion loss from port 3 to port 7, and here is our return loss from port 3 back into port 3. I'm going to cut our demonstration there, but feel free to reach out for any questions, and I'm going to hand this back to Matthew to wrap up our webinar.
All right, thank you, Roger. Okay, so let's finish off. We saw the demonstration, and what we want to move to now is just the final section. I have a small section here of a preview of a new 3D extraction engine that we're offering now as well. So first, we're going to review some of the challenges that we had with our existing 3D engine. So the reason it wasn't used with the solo time because speed is a big problem. Practical computational problems, large designs really make it pretty challenging to come to a reasonable solution. The reason for that is because this is how our solver tries to break the problem up. And what it does is you can have a master core, or that does the initial mesh, does the adaptive mesh, and once that's done, it's going to pass that mesh off to all the worker cores or worker distributed machines. And they're going to go through, and at each frequency, they're going to take that mesh and they're going to solve that matrix and get results. The problem with this is that each worker is going to need as much memory as the adaptive mesh takes up, which is generally large. So each of these machines are going to need to be pretty substantial for this to work. So it's tough to break this up. It's kind of challenging. Our 3D solver that we originally had wasn't made with dispersed computing in mind necessarily. So we came up with a new one just recently. It's called Clarity, and it's made with parallelization in mind. So multi-threaded core, no problem. Distributed processing, send it out to multiple machines, no problem. Send it off to cloud resources, again, no problem. It's high capacity, so you can now still solve large structures on any computer. It is still an intense process, but the parallelization, the ability to spread this off among multiple machines, has decreased the amount of time needed to solve this. And the accuracy is going to be identical. It's using the same techniques. We're just solving the mesh in a better fashion, and we're distributing the solving of that mesh to different machines in different fashions. So to give you an idea of how that works now, with the Clarity solver, it's going to take the data and do the initial mesh, and then it starts farming that adaptive mesh off to everybody else that's available, or all these other cores that are available to help. And that really reduces the amount of memory that's going to be needed on each of the machines, because it's now spread between a number of different machines. Once it finds a converged solution, it then does the same thing and farms that out to all these different cores that can now go through and solve at each frequency point. And again, you have multiple cores doing each frequency, meaning that they can have smaller portions of the overall problem and get to the results. Some of the things that you can solve with our 3D solver, and you could have done these before as well with our existing 3D solver that Roger showed and that we have. But HDMI connectors, so if you have connectors and you have a model of that connector and you want to solve that, that's something you can definitely do. So you can see the results. And then what you're seeing down here in the lower right is the comparison between the 3D solution and the Clarity solution. So the existing 3D and the new 3D with parallelized cores. Now, what is the benefit? We tried to quantify some of the benefit that was available. So we took a design here, and this one had about 62 ports, I believe, on it. So it's not the whole board, but there are 62 ports that we were taking a look at on this board. And with Clarity, 32 cores, so substantial number of cores still, and it took almost a day, less than a day. The traditional 3D solver took multiple days. 168 hours is how long that one took. So a performance gain of almost 8 times. And when you're talking about this amount of time, the ability to do something in a week versus a day, that's a substantial increase in time and the ability to do more simulations and more analysis to make sure that everything is working. So this increase in performance, decrease in simulation time is critical. Also, the Clarity memory requirement is reduced as well. So it needed 25 gigs of memory, still lots, but not as much as the full 3D solver needed. One more example that we had. So in this case, we did a full board, or nearly a full board, 64 signals across 8 PCBs. So a lot of stuff that we're taking a look at, packages going all over the place, our packages and mills. And the number of cores used, 128. On Clarity, that took a little over a day. On the legacy one tool, it wasn't even able to mesh it. So the machine that we threw it at, which was capable, wasn't even able to solve it. So now you have the ability to solve things that were previously not even possible to do in the 3D space. You can do it now. Substantial memory, again, required 52 gigs. So lots required there, lots of cores required, but now you can start solving these problems where you potentially weren't even able to before. All right, so Clarity, just wanted to introduce it to you. It's the next gen 3D solver that we have, and it still has the accuracy. It has the same accuracy as the 3D FEM tool that we've had for a while. world-class parallelization technology. It was parallelization in mind. That's one of the big things that it was designed for. Made with up to 10 times performance. We have a number of benchmarks from customers, and we get a range usually between 7 and performance gain. So lots of speed increase, integrated still with the Cadence tools, and it's even available in the cloud. So if you want to upload that to the cloud and have the cloud simulate that, you can do that as well.
Thank you, Matthew. At this time, I would like to open the floor for the Q&A section. Please enter any questions you have into the chat now. If we are unable to address your questions immediately, we will be in contact with you. Okay, Matthew and Roger, I have a couple questions here. So someone wants to know, how do you evaluate how accurate you need your simulation to be?
Good question. So you can, the amount of accuracy that you need is often dependent on what simulation speeds you're simulating to. So if you're just simulating low speed signals, your simulation accuracy doesn't need to be incredibly high in the high frequency range. So that's one thing. And the type of design that you have and perhaps necessitate different solvers. So what you can do to figure it out is you can run hybrid type analysis and see how that one works and see the results you get with that. And then often you're going to use the 3D solver for sign off. So just at the end, you're going to use that type of solver just to verify that everything does behave as you believed it to. So take your time at the end to do one last result, and hopefully your results are going to be similar. If they're not, then you know that you need to dig in a little bit more and find out some new problem.
Okay, thank you. We are running a little short on time, so I'm going to ask one more question. Someone mentioned, ideally you would simulate all nets on your PCB, but often there may not be enough time. How do you decide which nets or interfaces you should give simulation priority to?
Okay, yeah, good question. So that's often people's desire to simulate the whole board. That is nice if you're able to, and that's often what the FDTD solver is for that I mentioned right at the beginning. So that type of solver is good at simulating the whole board, and usually, hopefully, it's going to help you identify areas that need further analysis. So using that tool, it's going to tell you areas that may be problematic, and you can focus some additional scrutiny on those with some of the other solvers. Or perhaps you have signals that you're aware of. Often the case, I find that users are aware of which signals are going to be problematic, the ones that are going at high speeds, the ones that need special shielding around them. Those types of traces are usually the ones that you're going to pay a little bit extra attention to and make sure that they're working well. So a combination of things you might find with the full board solver and things that you already know from design to be potentially problematic.
Great, thank you. That was very informative. It looks like we still have some questions coming in, but unfortunately we are out of time for today. However, if anyone has questions that were not addressed during the webinar, we will be following up with you on an individual basis. We will be sending everyone a recorded version of today's webinar with the slide deck within the next few days. Before we sign off, I would like to inform you that our next webinar, DDR Design Guidelines, will be next month, so please keep an eye out for information on that. Thank you for taking your time and joining us today.